Hello, and welcome to A Bit of Tech, a Nokia Bell Labs podcast celebrating our centennial. I'm Aron Heller, and I hope you've been enjoying our journey through where we've been, where we are, and where we are going. Bit by bit on this podcast, we've been unpacking the past 100 years and exploring the next. A quick reminder to catch up on all our previous episodes on our dedicated landing page, and please do like, rate, and subscribe to the whole series on our various platforms. That's Spotify, Apple, Amazon, YouTube, and many more. In past shows, we've provided a comprehensive overview of Nokia Bell Labs and taken individual deep dives into our unique roles in AI, quantum, and space communication. In this episode, we're going to spotlight our core research, the foundational communication technologies that govern our world, and for which Nokia Bell Labs is most well known. We have been at the forefront of communications throughout our 100-year history. In 1947, for example, we established the cellular concept, and the following year, our own Claude Shannon laid down the fundamentals of communications when he introduced the fields of information theory and coding. Over the years, we've also pioneered groundbreaking research in optical networks, software systems, and semiconductors. But of all this wide range of technologies, we're going to specifically focus today on wireless communications. In particular, we'll review the journey we've made from 0G to 6G and discuss how Nokia Bell Labs has been instrumental in its development every step of the way. And it's perfect timing to discuss all this as we head into our premier event of the year in early November, the 12th Annual Brooklyn 6G Summit. It's a marquee meetup in which leading voices from technology, business, academia, and regulation come together to shape the future of wireless and the 6G era that awaits us toward 2030, and that aims to fuse together the physical, digital, and human worlds. So to get into all this and much, much more, I'm very pleased that our guest today is Harish Viswanathan, the head of our Radio Systems Research Lab. Harish, welcome to A Bit of Tech.
Hi, Aron. Thanks for having me. Good to be here.
Good. It's great to have you, and I know that you're the right person to do this. This is your area. First of all, though, before we get into this journey, let's talk a little bit about yourself and your role at Nokia Bell Labs.
Sure, yeah. I've been in Bell Labs for a long time. I joined Bell Labs in 1997 after finishing my PhD at Cornell University. Right now, I'm the head of Radio Systems Research Lab. In our lab, we have people working on radio transceivers, antennas, power amplifiers, filters, and then we have people working on the signal processing, both digital signal processing as well as baseband signal processing. And then we have also people working on radio resource management. And we generally work on the different generations. I joined, it was 3G, but yeah, since then we've been working on these things.
We're going to take a whole journey there all the way through. Before we jump into those Gs, all the different generations, I want to just talk to you briefly about the whole overall theme of foundational technologies. It's one of the main things we're focusing on our centennial here. It's a very wide scope, and it entails a lot of different fields. Could you give us a quick overview about what it is when we really talk about foundational technologies?
Yeah, that's a really good question. Foundational technologies for communication systems, I would say, starts with maybe information theory. So that's sort of the mathematics of communications, and mathematics is the foundational science. Other than information theory, all communication systems rely on coding techniques, modulation techniques, waveforms. Then coming to wireless specifically, I would say the foundational technologies are more on the analog front end, things like antennas, amplifiers, filters, as well as now MIMO or multiple input, multiple output technology. And then for optical communications, it would be the lasers, again, amplifiers, multiplexers. So lots of things. And then, of course, devices and material science plays a critical role. We could even say the transistor is a foundational technology for all communication systems.
We'll get into all that. Obviously, this is a huge, wide range. I'm glad that you're with us here to go through it. And like I said, we're going to focus on wireless here. So as we usually do in this podcast, we start with a bit of history. And I guess we'll start by going way back to 1947. A lot of people remember that year related to Bell Labs as the year that we invented the transistor. But it was a very busy year here at our Murray Hill, New Jersey headquarters, because the same year, we also came up with the original cellular concept. And some people refer to that as 0G or the pre-cellular era. Could you tell us a little bit about the genesis of that?
Yes, yeah. Back in 1947, we already, of course, had wireless communications, but it was very limited. It was limited to just emergency communications. Perhaps it was, of course, used in the military context. But what they were already thinking in Bell Labs is how to increase the capacity of wireless communication systems. We only had technology that could use a limited amount of spectrum, and we had to increase capacity. So right then, uh, Young and Ring in Bell Labs in 1947, they came up with this concept of frequency reuse. So the whole idea behind dividing a geographical area into cells and being able to reuse the same spectrum in multiple cells was invented here in Bell Labs, and that is even today the basic underlying approach to cellular communications.
Let's jump forward to a few decades, the 1970s. That's when it became commercial, and that's what's often referred to as 1G. Now, this essentially is when cellular is in the analog age, right? And it's the first commercial deployment. We were also involved in the first 1G trials, right?
Yes, that's an interesting story there. So Marty Cooper from Motorola was leading a wireless team that actually made the first wireless phone, usually called the Brick, and he actually made the first call to Bell Labs to sort of prove that they were the first to invent the phone. But yes, that was the era of analog communications, called the 1G, let's say, lasted till the end of the 80s, I would say. And yeah, we used large radios, size wise, they were big. And, recently I saw an article where, it said it cost a lot of money to buy one of those phones. One had to work, an average American had to work 456 hours in order to be able to buy one of those phones. And today it's only about 9 hours of work. So I think you can imagine what it would have been like at that time.
That's very cool. And also that story about Marty Cooper, we know that it was this race with Bell Labs, and he made the first call to sort of rub it into Bell Labs and say, I got there first. I know I'm going to see you at the Brooklyn 6G Summit. We mentioned Marty Cooper was the winner of the 2017 Pioneer Award, and this year he's getting the Marconi Society Award. So it all goes back to the beginning of this phone. Let's move on to 2G. This is where we really start to enter the modern age, and this is around the 1990s. This is voice, SMS, the beginning of digitalization and browsing on the go. What was so significant here as far as Bell Labs' involvement?
There were two types of technologies for 2G, right? There was the IS-95 or code division multiple access technology that originated in the US, and then there was the GSM that originated in Europe. They were both digital technologies. I think the whole idea of digital modulation also originated in Bell Labs. We had a lot of people investigating various aspects of digital modulation, signal propagation, and these made it in parts to various technologies in 2G. From a user point of view, it was really starting to make communications devices available to everyone, right? So we had to move from analog to digital in order to increase the capacity of the voice communications. And we were able to introduce things like SMS, text, because it was all digital.
So I know this is a different iteration of Nokia back then, but people associate a lot that era with our old phones. The Nokia phones were very familiar to most people in the world at that time. Then we move on to 3G, and that's a real big jump. That's when the internet came to rival phone calls and texts on our phone. We're talking broadband, data, optimized voice. That was the era of the BlackBerry. It's when the iPhone came out. Even though it's a 2G device, it's very much associated with 3G. This is what I remember really as the big jump in Gs.
That is true. It was a big jump. I think one thing that's been true in the cellular generations is that each new generation is really optimizing the important use case of the previous generation, right? So optimizing as in reducing the cost significantly and increasing the capacity. So this is what 3G did as well. I think one of the biggest successes in 3G is how the price of voice call went down tremendously compared to what we used to pay for 2G. In addition, of course, 3G opened up the possibility to do broadband. Of course, it was the first generation where cellular broadband was deployed. Of course, it didn't take off. It started to take off towards the end of the 3G era with Blackberries first and other smartphones. So I think the broadband was made possible because you could go to wider bandwidths. So I think that's something that 3G introduced when compared to 2G. going to channels of 5 megahertz. Yeah.
Yes, this really like ushered in the era of mobile computing. It really sort of took it to a new level. All right, I guess we'll just keep on going by the numbers over here. We're up to three. Let's move on to four. That's the next generation, also a huge upgrade. In fact, it revolutionized media consumption. We'll talk about that. And an interesting side note is also the network that we currently deployed when we sent it to the moon recently. So it's still in most use. When I look at my phone, it's usually on 4G still. Let's talk about that, about our specific role in that.
Yeah, 4G had a lot of interesting things in it, right? We went from this CDMA or core division multiple access in 3G to orthogonal frequency division multiplexing. The waveform change is something that all the techies really point to as the big transition between 3G and 4G. And the reason for that is, of course, we wanted to go to even wider bandwidths, which actually enabled us to do things like video on the phone. So people started watching YouTubes. The smartphone really became a thing in 4G with all the apps. And another very important technology that came from Bell Labs is this what we call the MIMO, or multiple input, multiple output. That's a way to increase the spectral efficiency, or how much we can get out of a limited amount of spectrum, by being able to simultaneously stream multiple data streams. And this was invented here by Jerry Foschini and his colleagues in Crawford Hill here in New Jersey. And it was about the time when I joined. It was very exciting here in Bell Labs at the time. And we all worked on this MIMO technology. This was back, of course, in '96, but it took a long time for it to really make it to products, which happened in 4G, not immediately in 3G.
Yeah, we should mention that these generations typically they've been about a decade each one. So it's like the 3G was the 2000s, and then a decade afterwards was the 4G. And like you mentioned, that introduces all these things about video and also navigations and the variety of apps. And MIMO, could we just stay on that topic for just a little bit longer? Because I remember MIMO, the big influence was that it sort of closed the gap a little bit between the uplink and the downlink, right?
MIMO certainly helped both uplink and downlink. Of course, the demand was always for the downlink. Throughout the generations, other than voice, all of the data browsing and YouTube videos or other videos, all of that is really downlink traffic. So downlink traffic is still significantly larger than uplink traffic, almost a ratio of 6 to 1 to 8 to 1, etc. So the emphasis was always on increasing the capacity on the downlink. Yes, so MIMO was initially really used for increasing downlink capacity, but of course, over time, it's also been useful for the uplink. On the uplink, it's especially useful to increase the coverage, right? Coverage is basically how far out from a cell can you go and still maintain your voice call. And it turns out that MIMO helps there as well.
Great. All right. Well, we have finally arrived at the present. We've covered all of our past, and the present is the era of 5G. We're sort of in the middle of it right now. That is a major change with ultra fast data, low latency, devices that are connecting seamlessly, the whole IoT world, the Internet of Things. We're in the midst of it. Where do you see its significance in this whole history, this whole line that we're talking about here?
Yeah, 5G introduced massive MIMO. That's another technology that was invented in Bell Labs in the 2010s to, ultimately the paper was published, I think, around that time. Tom Marzetta here was working in Murray Hill in this very building from where I'm talking to you. And that became one of the biggest successes, I would say, in 5G. It enabled, especially in the US, fixed wireless access growth, because we could now afford to have wireless achieve very high data rates, as well as just raw capacity in terms of megabytes, right? So that, I think, is a big change. So in general, 5G has increased the speed, has increased the amount of data everyone consumes. So a lot of the plans now can be unlimited data plans because we have 5G. I think that's the biggest change consumers see. But 5G, of course, can also be really applied to the industrial automation. We have standardized ultra reliable low latency that can really help change some of these factory automation to wireless solutions instead of having fiber optic solutions. So that's a use case that's still expanding, I would say. There have been limited deployments at this point, but I think that's going to also potentially take off in the future.
Okay. So we have one more quick pit stop before we get to the future, which is really the focus of our research right now. And that's something that we call here 5G advanced. It seems like that's kind of like a gateway between 5G and 6G. And since we're now in the year 2025, we are essentially halfway between these two generations. What exactly is 5G advanced?
Right. 5G Advanced is sort of the half generation after 5G, you could say, right? Typically, we have uh, an intermediate upgrade, which is backwards compatible. So you don't really need new spectrum or new phones. So with 5G Advanced, it's really about three things, right? Better efficiency. So there's a lot of effort devoted to increasing the energy efficiency, increasing the battery life of devices. Then it's about improving the experience. So here we're talking about new technology uh, like quality of service improvement for AR, VR, the augmented reality, virtual reality, extended reality sort of applications. So there are special features in 5G Advanced for those sorts of applications. And then the third is really extension, going beyond the traditional applications, making 5G even better for other verticals like car to car or railways, mission critical applications. So these are some of the things that are prominent in 5G Advanced. Of course, we also enhance other capabilities like MIMO. Actually, as you pointed out, increasing or applying MIMO for uplink is one of the new features in 5G Advanced, as well as transmitting from multiple base stations. What is called the multi TRX. That is also another interesting feature that increases the resilience and robustness of 5G.
And it's also introducing a lot of the AI and ML that we didn't have before in previous generations.
Yeah, actually, that's a good point. What we also do typically in these generations is, start trying out the things we really think are going to happen in the next generation. So we have a lot of discussions in standards bodies like 3GPP about AI and ML, and also non-terrestrial networks. These are all heavily discussed, and even some of the specifications are done. But most people generally believe that these will really take off in the following generation. Right? It's almost like work that's being done in preparation for what should come next.
Well, it's a great transition because we've covered all the past and the present. We finally arrived at the future. That's where Nokia Bell's research is always most focused. And this future 6G network, it makes up most of our current research. It's described as an extrasensory network where the physical and the digital intertwine. Very exciting. It sounds like. What exactly does that mean in practice?
Right. I think it's about immersive communications, right? Or holographic communications, right? So, what it means is we want to have digital experiences that are almost as good as physical experiences. So, imagine being in one place and being able to experience another place as though you were there. So, and this is possible with very rich three-dimensional video communication. So you need a real-time, highly spatially accurate digital representation of the physical world that you can then send to any place to the user to experience that. I think that's how we want to achieve this sort of unified experience across digital and physical worlds. And what that means is a lot of capacity on the networks. And of course, we also need new devices to enable that, right? The smartphone is definitely still going to be there for a long time, and it might be the conduit to the network, but we will have new user interfaces like the smart glasses that will help us have these unique new digital experiences. So that's one of the primary motivations for 6G.
All right, this is our core research. This is really like the emphasis that we have right now, and it's really Nokia actually leads the share of voice in that discussion. So it's something that we're very, very focused on. I know that we have a lot of different research areas that are related to this, and I was hoping we could start breaking them down a little bit. We're going to have a whole other episode, by the way, on sensing, so we don't need to get too deeply into that. But I know that there's something called ISAC, right? ISAC, that's digital physical fusion related to sensing. Could you discuss that a bit?
Sure. Yeah. I mean, there are many different technologies that are really new that we are going to introduce in 6G, and the integrated sensing and communications is one of them. So what that is to enable these cell sites or base stations to not only perform the communications function, but also perform the radar-like sensing functions. So we are at the point in the evolution that there is sufficient bandwidth to get very good range resolution on sensing. So sensing works by capturing the reflections off of these passive objects. And when you pick up these reflections, you can sort of tell how far away they are from the base station by measuring the time it takes for the signal to propagate to the object and back. So since the bandwidth is large, we can get very good time resolution. So that's one reason. And the second is we have massive MIMO deployed on all the base stations, and that enables us to do good angular resolution because you have beamforming. So for these reasons, it's now the right time to explore introducing sensing functionality from the base station. So that's what we are working on, and yeah, it will likely happen in the 6G time frame. Yes.
Now, another element of the 6G time, and you'd mentioned is going to be huge performance leap. Obviously, that's always included in the generations. We talked about MIMO. You talked about massive MIMO. Here we've got something called extreme MIMO. What's the difference between all these? That sounds exciting.
Yeah, I think going back to massive MIMO versus MIMO, the difference is really in terms of the number of transceivers, number of antenna elements, and the number of simultaneous data streams that one can transmit in a given amount of spectrum. And with extreme massive MIMO, we are taking it up another notch, right? So in 5G, typically we have about 192 radiators and something like 64 or 128 transmit receive chains, but we want to take that to thousands of antenna elements when we go up to 6G, and that allows us to do even more simultaneous streams. And there's a lot of things that have to be engineered for this to work correctly. So we want to conserve energy as much as possible to keep the size, weight, and power consumption of our radio units still within reach, right? So I think these are some of the things that are being addressed today, and that will result in basically very high spectral efficiency. So again, very high capacities using the same amount of spectra.
We'd mentioned before when we were talking about 5G advanced how that really starts to incorporate the artificial intelligence, the machine learning. But 6G, that's when it's really going to become a game changer, right? Like that's when AI is really going to be AI native, so to speak.
Exactly. So another big advance in 6G is going to be this AI native. What that means is we want to use AI as a tool, AI for RAN, AI for core, AI for the device at the level of the communication system. So every function could potentially leverage the AI tools. We have the latest and greatest models that can be incorporated even down to the physical layer to improve the spectral efficiency, and certainly at the network management level for automating the networks. Intent-based network automation is one of the key technologies that we will see in the 6G timeframe. And going down the layers, things like radio resource management can be done more efficiently using artificial intelligence techniques. And then, as I said, in the physical layer as well, signal processing can be potentially replaced with some new ways of doing that. So, and then we also expect the devices to be capable of doing such things. And together, I think we will achieve quite a bit of advance in terms of operational efficiency and automation.
Now, all these things that we're going to see in 6G, obviously, it's all this impressive technology, but there is a cost to it. It's going to be a lot more dependent. We're going to need a lot more energy for it. And that brings us to the fourth element of our research here, which is sustainability, because we're going to have to figure out a way for this not to burn up so much resources. And that's why we have something called ASIC, right? About energy efficiency. What's that about?
Yeah. So where does all this computing happen, right? So the computing happens in what is called the application specific integrated circuit, or ASIC, or system on a chip, which goes into our base station products, right? And we want to make them more energy efficient. So we're exploring a lot of new technology around how to build these SoCs much more energy efficiently. Introducing things like power islands or compute in memory techniques, and building accelerators for specific types of computing, like the matrix vector multiplication, etc. So this is how we think down to the ASIC level we can make significant improvements in energy efficiency. Of course, the energy efficiency will be addressed at the system level as well. can we make the energy scale with the load, right? So zero load, zero power. That's what we should try and achieve.
Our next episode is going to be devoted entirely to sensing. So it's really interesting because that has a very direct link here to the 6G and the sense of that the 6G network is supposed to be able to intuitively sense its object and its movement and everything around it. So that's a real differentiator. And as I mentioned in the intro, this is an excellent time for us to talk about it because it leads us right into the Brooklyn 6G Summit, the beginning of November. I'm going to be there. I know you are as well. So we're looking forward to seeing you there as well. Let's talk a bit about the main things that are going to be coming up at the summit. I know the theme this year is called Building What's Next, and the big focus is on AI and value creation.
Yeah, I think Brooklyn Summit is a very interesting conference. It's been running for over 10 years now, and we project what the future is going to look like in that. We invite a lot of interesting speakers from operators, partners, Nokia, and we talk about what 6G is really going to be about. So I think this time around we have a very interesting lineup of speakers talking about AI and also how does 6G really generate value for operators, for consumers, for industry. These things will be discussed there. Yeah.
Well, we hope that our viewers and listeners can, if they can't get there physically, at least they can tune in. We're going to have a roving reporter. We're going to have summaries of each day. There'll be a summary blog. We'll also have interviews with the participants. So we have a lot of excellent coverage from the Brooklyn 6G Summit, and we hope people will be able to join us for that as well. All right, so let's talk now, I guess, about we're getting to that 6G era where it's going to become commercial in 2030. Now we're at the stage, essentially, of the standardization and the advanced research. When it becomes a reality, what are the main use cases that we are going to see when it comes to 6G?
Right. So if we start talking about 6G day one, I think we'll start with the immersive communications and gaming. These are some of the applications that can make use of the high capacity and data rates. Then we will see certainly increased use of 6G for fixed wireless access wherever it's needed. I think 6G has the potential to further reduce the cost per bit substantially and make it more competitive with other types of home broadband. So certainly that's an interesting use case. I think by the time of 6G, we'll also see increased adoption of cellular technology for industrial automation, mining, and other verticals. So I mean, some of those will directly deploy 6G. And then of course the sensing that we talked about has very nice new use cases, which may come a bit later, maybe not in 2030, but sometime during the 6G generation. And there we could think of use cases like drone detection. A lot of municipalities and governments are now very keen on having some technology to do drone detections, for example. So I think these are some of the use cases that I can think of at the moment.
There's also going to be a whole bunch of different devices, right, that you can use in the 6G era that we don't have now?
Absolutely. I think if you look at the smart glasses, as I say, I mean, they're being continuously improved, reduced in cost. And I think it is going to reach a point where it becomes mass market. I mean, we may not be all wearing it all the time, but we will all find, I think, real use for that in various things that we do. I think that's something that's going to be a new device. We can also think of new low energy devices, right? Like things that rely on just the ambient radiation that's available, like electromagnetic radiation, and using that to be able to signal something to the network, so we can locate devices, zero energy devices. So that might be happening more in the indoor domain. Then we could also think of really looking a bit further, robots, right? There are all kinds of robots that people are working on. So they may all have their own connectivity. We may see robotic delivery, not just drones, but also on streets. You could have robots running around that are designed for delivering items. So those will have their own connectivity. Yeah, one more new type of device could be AI enabled handset, or sort of not the traditional smartphone, but some other type of device that relies entirely on AI for all communication. So it's basically voice and actions that it can recognize. That sort of a device is also possible.
All right. Well, like I mentioned, we had a whole episode also about AI previously, and that's going to feature prominently in 6G. It's really a huge feature on that. But I have to segue a little bit with you on a bit of a critical point here, which when I talk to people about the 6G summit and 6G, a lot of people are like, what are you talking about? We're in 5G, and a lot of places that's not even deployed. And so I guess some people out there would say, why do we even need a 6G?
That's a good question, but I think there's a significant evolution in technology, and there's an opportunity to reduce the cost per bit. I would say that's something that is very valuable over time. We all consume a lot of data, and I can only see that growing. Right? I mean, if you want an example, today we are exchanging emails with attachments that are like 10 megabytes or even more, and you couldn't imagine doing that 10 years ago. So things like that drive the demand for data, and I think there'll always be need for more consumption, more data to the devices, new types of devices. And so we do need a new generation that incorporates all the technology advances uh, in a non-backward compatible way. So we can design the best systems out there for 6G. Yeah, so I do think there's a lot of opportunity for new use cases and for reducing cost. So that's the reason for 6G, I would say.
And each one of these generations tends to sort of align with what we call the different industries, the industrial revolutions. So that was the last one, was the Industry 4.0. Now we're talking about 6G will align with Industry 5.0, and all these new things that will be very revolutionary. And one of them I hear a lot about through Nokia Bell Labs is something called digital twins. And I know we've got a lot of research into that and a lot of projects on that, which basically is like this replica, which can make an industrial site or a city. Could you talk about that a little bit and what kind of impact that's going to have on people?
Yeah, it's a very good question. Yeah, digital twins is a technology that's just starting to happen, especially driven by the AI technology as well. So what digital twin is, of course, a very good or high spatial resolution, real time representation of the physical environment. So it could be for example a warehouse or a factory, right? And what we can do is synchronize. So let's take the warehouse example. So you would have a digital twin of a physical warehouse, and in the digital twin you can actually query, and you can use your language to query things like, okay, where is this box located in my real factory, right, or real warehouse. But the digital twin can answer questions like that, or how should I go from where I am to reach this particular box in the warehouse. So we can connect the large language models to these digital twins to answer such questions. That's one application. But even within 6G itself, digital twins are likely to play an important role. Like part of automating 6G would involve having a very good representation of the network digitally, right? Knowing where all the base station sites are, even where all the devices are, and how we should, modify the network to make it even better for, say, a special event. Uh, like the inauguration of the US president or something like that, then we want to modify the network to adapt to the new traffic conditions. So for things like that, I think a digital twin and a geospatial digital twin, where we even model the radio propagation as part of the digital twin, would be very useful.
I want to touch on one more thing that I know that you're involved with and sounds like it has far reaching repercussions, something called semantic communication. What is that?
That's the latest technology, I would say, for communications that goes after the real meaning. So back when Shannon talked about information theory, he had three levels of communications. That's the one that was the engineering or symbolic level of communications, where you just treat symbols as what they are, and that's what you try to communicate. But if you think about human communication, what we're really after is communicating the meaning. So when I want to communicate with you, I want to convey my meaning to you. And the next level, even above that, is communicate what you actually have to achieve as a goal. So if I want you to go pick up an object, that's my goal, and I am communicating for that goal. So that's called goal oriented communications. So semantic communications is actually trying to extract meaning from the symbols and then communicate just the meaning for a specific goal. So that's what semantic communications is. And if you think about why it's so important now, it's because most people are familiar with large language models, and you can see that these models are sort of able to understand what you're saying. They extract the meaning out of your prompt, for example. So I think we are at the point where we are able to extract meaning out of all kinds of things: images, video, text, and just communicate that. And that's what makes semantic communications really interesting at this point.
So instead of just the raw data, the zeros and ones, the bits of Shannon, it's really what they mean. We can sort of like understand the utility and effectiveness of them.
Yes, exactly. And the advantage of doing that is that you have to communicate a lot less. So you can compress your video or images a lot and use generative AI techniques on the other end at the destination.
Now, before we wrap up, I want to have a chance to ask you a couple of personal questions as well about your background here. What's your connection to it? Did you grow up on this? I know that you said that when you were younger, you had an early connection to this, even growing up.
Yeah, I always loved mathematics. I think for somebody who wants to be an engineer and who likes mathematics, I think this is a great field because it combines, a lot of interesting concepts and makes it real, right? I think that's what I find most attractive about wireless communications. And of course, yeah, I mean, once I joined Bell Labs, it's been really exciting to see all the great inventions and also how they get productized. So it's been a fantastic career for me.
Excellent. Well, let's leave on this question here. We try to end with something forward looking. And we always say here that it's impossible to imagine the past 100 years without Nokia Bell Labs. And I'm sure that's true also for the next 100 year. But try, if you can, to paint us the future regarding these foundational technologies. And I guess the best question to wrap up this podcast would be to ask you whether there's going to be a 7G and what that would look like.
Yeah, I think there will definitely be significant technology advances. We are not going to stop advancing technology with 6G. Whether we call it 7G or something else, I don't know. But for sure, there's a lot of room for further enhancements. I mean, we just are starting to scratch the surface of things like semantic communications, even, AI applied to communications can become much broader and deeper in terms of how systems can learn to communicate themselves. And of course, we can still do better in terms of what we get out of the spectrum. Maybe other things like reconfigurable intelligent surfaces start to become important. So yes, there's a whole lot of technologies that are out there. And I mean, the ultimate goal would be, yes, this unification of the digital, physical, and human worlds. And while 6G will make an initial or somewhat reasonably achieve that, but there still will be a lot of room beyond that.
Well, I could go on with you. This is very fascinating stuff, but we are out of time on this podcast. We've got another episode planned for later this year. As I mentioned, that will focus on our vast scope of sensing. In the meantime, thank you, Harish, for joining us. A special thanks to our producers, Melissa Aiken, Zainab Zakaria, and Oliver Hodges. And thank you to everyone who tuned in for this episode of A Bit of Tech. Please be sure to subscribe, follow, and like us on whatever platform you're getting this podcast, and do stick with us as we continue our journey throughout the Nokia Bell Labs Centennial Celebration. Until next time, I'm Aron Heller. See you soon on the next episode of A Bit of Tech.